Okay, I think people have joined, so we'll start today's webinar. I'll share my screen. I hope my screen is visible. Rahul, Joel, is my screen visible?
Yes, it's visible.
Great. So, good evening, everyone. Good evening for the people who have joined us from India, and good morning and good afternoon for everybody else from the rest of the world. So let's begin. So today's exciting topic is a liquid pressure recovery factor prediction using autonomous valve CFD. So let's have a go. So before starting, I would like to introduce myself. I am Akshay. I'm the business manager of AVC. AVC is the product that we have developed at Simulation Hub CC Tech. So I started as a CFD engineer. I have extensive experience of near about 4 years now in CFD. Just recently started taking up, you know, understanding the business aspects of the industry, and it has been a fun experience for me so far. Lots more to learn, and uh, we have our young, talented teammate, Joel. So Joel is a CFD engineer at Simulation Hub. He works closely with the product, with also supporting the users of AVC. He understands the problems and resolves them with CFD, and uh, he has done his BTech from VIT Chennai, and he has almost a year of experience in CFD now. So let's jump into today's agenda. So this is today's agenda. We'll try to understand what is choking of flow. We'll then see how it relates to cavitation. Then we'll define the liquid pressure recovery factor. Then we'll see why exactly does FL matter and how to find FL. Then we'll look at how AVC helps valve designers to get good valve performance from their designs. Then we'll have a look at some exciting case studies, and we'll have a look at the success stories, and we'll have a nice Q&A session. So without further delay, let's go and understand the liquid pressure recovery factor. So before jumping directly into the coefficient, liquid pressure recovery factor, or which is called as FL, I would like to start with the building the understanding of FL, why FL is calculated, and what leads us to FL. So let's start with a simple valve, which is an orifice plate, and the flow is an idealized one. Just to start in a simple manner, we'll assume this is an ideal flow. So we'll plot a few things along its length. We see the area. So along the length, the area varies. It reduces and then increases back again. Similarly, we also plot the velocity. So it stays almost flat before the orifice plate, and after it, it jumps to a high value. And this can be understood from the simple mass conservation. So uh, since the flow rate has to remain same, where the area is small, the velocity rises to keep the flow rate consistent and to follow the mass continuity. Similarly, we can plot the pressure. So we see that the pressure starts at a high value. It gradually decreases near the orifice plate, it hits a minimum value, and post the orifice plate, it recovers and starts to reach the outlet value. Now, the interesting thing here is the velocity is peaking and the pressure is dropping. We can very well understand this using a idealized case. So near the vena contracta, the area reduces, the velocity rises, the pressure dips, and we have our friend Bernoulli to explain us this. So this is the conservation of mechanical energy inside a flow, and near the vena contracta, the pressure dips, that energy gets converted into the velocity head here, and further downstream, as the velocity, as the area gets back to the original size, the velocity is then transformed into the pressure. So Bernoulli helps us understand this relationship between the dip and the fall of pressure and velocity respectively. So again, this is the idealized case. This is running at one velocity. We increase the magnitude of the velocity, and then we'll try to plot it on a flow rate versus square root of pressure drop plot. So as we guessed, the relationship between flow rate and pressure drop is linear, meaning as the pressure drop increases or decreases, the flow rate also increases and decreases in the linear fashion. So in an ideal world, this graph would continue to any flow rate and any pressure drop. So now a slope of this line we generally refer to as CV. But this is the ideal case. What would happen if we do it in the real world? So to understand that, we again have two scenarios where the blue curve represents the first uh, pressure drop and the second curve represents the higher pressure drop. So we introduce here something called as PVC. PVC is the pressure at vena contracta. Vena contracta is the area where it's the minimum. And we are seeing here that the pressure drop for the second case is higher than that of the first case. Now, if we continue doing this, as we saw in the previous plot, if we continue going up the straight line, will the plots also shape like this? Will these situations also replicate in the real world? Now, to answer that question, we'll have to take a real example. So in real life, what will happen is, let's say this is the case where it's uh, a normal pressure drop. We start increasing the pressure drop and we keep on increasing till it reaches the gray line, which is the vapor pressure. Now, as soon as the pressure in the domain goes below this, thermodynamics kicks in. And as we see from this phase diagram, this is a representative image, that once the pressure, the minimum pressure in the domain falls below the vapor pressure, phase change happens. So this is where things will start to, get really interesting, because, we have a phase change, and this phase change in the flow is generally referred to as cavitation. So cavitation is formation of vapor bubbles. So as the pressure inside the domain is falling below the vapor pressure, this leads to phase change. And once that phase change takes place, small vapor bubbles are formed. Due to the advection of the flow, these vapor bubbles are then carried downstream where the pressure recovers, and it causes a violent implosion of these bubbles. So cavitation takes place near the vena contracta, it is the place where the the flow velocity is the highest, the area is the lowest, and the pressure is also the lowest. This is where the bubble formation takes place, and then it is advected downstream. So if you see the curve here, at this point, the flow, at this point of the flow, the pressure starts reducing. It crosses the vapor pressure. Then, as the flow carries those bubbles ahead, as the pressure recovers, it the bubbles implode or collapse into a violent implosion, and the pressure recovers. So cavitation is where the fluid pressure reduces below the vapor pressure and bubbles collapse downstream. This phenomenon together is called as cavitation. If the pressure never recovers to a pressure above vapor pressure, then such flow will be referred to as flashing. So the impact of cavitation is it leads to material damage. So high velocity jets, as you're seeing in this animation, the micro jets, they impact the internal surfaces and can cause a lot of damage. As the intensity of cavitation increases, there's a lot of noise generation, a lot of mechanical vibration, and it can really impact the flow effectiveness, meaning how your valve performs under such circumstances. It really impacts the valve performance. As you can see, it really damaged this trim. So, it's a very real effect, and it is a very detrimental effect as well. It causes a lot of material damage, and this could lead to many other problems further downstream. It could in loss of equipment, in loss of material. All of these things could happen. So it's a very real uh, thing that we need to take care of. So generally, cavitation is measured, and it's done using accelerometers and pressure transducers. So the amount of vibration and mechanical noise generated during this is measured, and their intensity gives the different levels of cavitation. So incipient is where it just starts, constant is where it's at a constant rate, and then there's the choke-in cavitation. So the green zone is where the flow is non-cavitating, and the red zone is where it starts cavitating, along with various degrees of cavitation. So back to our choking flow condition. So we saw that if the vena contracta pressure is well above the vapor pressure, the flow is not cavitating, everything is fine. Once the vapor pressure uh, is crossed by the pressure in the domain, by the vena contracta pressure, and it regains its pressure back to the outlet pressure, this would we would refer as a cavitating flow. So cavitation is taking place here, but uh, there's no flashing. So if the downstream pressure never recovers above the vapor pressure, we would say this is a flashing process. And the intensity of cavitation increases from a cavitating flow to a flashing flow, and this flow would be referred to as a flashing one. So let's take a look at what actually is happening and why the flow actually starts choking. So in a non-cavitating flow, everything is fine. Then we introduce the concept of vapor pressure, and we see that there are small bubbles forming here. So due to the domain pressure going below vapor pressure, there's a formation of bubbles, and they form at the vena contracta, and they're advected downstream. So let's say we increase the pressure drop further. This would lead to more cavitation and more bubble formation. And this, what it effectively does is every excess pressure energy added, let's say from the second case, we are adding some excess pressure drop here. But that pressure drop, that excess energy is going into phase change, noise, maybe some vibration, maybe some heat dissipation. So it doesn't lead to facilitating the flow as it would be before the cavitating zone. If we further increase the pressure drop as we do in the third case, the added excess pressure energy again goes into more bubble formation, more vibration, more noise, and effectively what is happening is these bubbles, if we go from case 2 to case 3, start to effectively form near the vena contracta, thereby reducing the size of vena contracta. And again, it's literally choking the vena contracta. It's literally not allowing more flow through the vena contracta. So this is what we would refer to as a choking condition, where increasing pressure drop no longer increases your flow rate. So we see that the bubble formation near the vena contracta effectively forms zones near the trim and the seat, and there it will start to reduce the effective area of flow, thereby reducing the flow instead of increasing it with increasing pressure drop. So just to bring all the points back to where we started with the non-cavitating flow. Then we saw what would happen in a cavitating condition and when it would be an excessive cavitation. So again, as we started with a idealized situation, now we move to a more real one. In this case, we'll also plot the flow rate versus pressure curve for these three scenarios. And what we would observe is up to a certain point, meaning from non-cavitating to just cavitating flow, the linear relationship between flow rate and square root of pressure drop is followed. Ideally, it would just keep going, but as we have seen, that wouldn't take place. What would happen is up after a certain point in the flow, meaning just starts to cavitate, this point, it will start to deviate from its ideal path and start becoming flat. So this point where the deviation just starts to happen is called as the incipient cavitation. And if we keep on increasing the pressure drop, we see that the curve is kind of flattening. There's no effective flow increase after a certain pressure drop. This would be we would refer to as choked flow, and the corresponding pressure drop would be the choked pressure drop. So since the flow is not increasing, it's becoming flat. And if we plot it, we would get the maximum flow rate through this valve, where the maximum flow rate and the ideal CV curve intersect. That is where we say have calculated the FL. So this intersection we would refer to as FL. Now we'll see how to get this value. So before that, we'll define the factor itself, the liquid pressure recovery factor. And it is basically the coefficient that quantifies how much pressure is recovered after it goes through the vena contracta. So it will be the ratio of the vena contracta, the pressure drop in the choked condition to where it is between the upstream and the vapor pressure. So the numerator would be the uh, difference between the upstream and downstream pressure, or the choked condition, and the denominator is the difference between the maximum pressure difference, which is the vapor pressure and the upstream pressure. FF is a factor which is multiplied here. So we are referring to as FL, but it's also called as a recovery factor. So what exactly is the recovery here? So as we have seen, it dips below uh, a certain minimum. So it starts upstream, it goes to a very minimum value, and then it regains its pressure. So this regaining of the pressure after the vena contracta is referred to as pressure recovery. So we quantify this recovery using, or which is referred to as TFL. So now a question to ask is, okay, uh, we have gone through the choking condition, we have gone through the uh, various understanding of cavitation, the intensities of cavitation, then we have also defined FL. We'll also have a look at what it refers to in the real world, in the case of real valves. So what FL quantifies, we have seen, it is the ratio of the uh, pressure drops, and we can see that it depends on various factors. So different valves will have different recoveries. So globe valve usually has a very low recovery, and ball valves usually have a very high recovery. Even two valves of the same type, meaning let's say they are butterfly valves, but they are, two different designs, even they would have two different FL values. Not even the FL depends on the geometry, it will also depend on the opening, because it's directly related to the vena contracta. So as we have already seen that the vena contracta determines how much flow will go through the wall. If it changes as it does in this plot from 10% to 100% opening, the FL also changes. So it's not a universal constant for a wall. It will change depending on the fluid properties, depending on the opening conditions, depending on the design. Let's say you add some, you retrofit some uh, trim, some cage, some orifice plate, everything changes in the system. So the FL of that system will change. So why does FL matter anyway? So going back to the question I asked, okay, we have gone through choking, gone through cavitation, defined this FL, but why does it matter? What's the use of this FL? So I would like you to understand that we can size valves using CV pretty well. CV will give you how much flow a valve can allow through itself at a given pressure drop, or vice versa. But here is where FL comes into picture. FL kind of gives you what is the maximum flow rate that can go through the wall. So it kind of gives you a pre uh, prediction as to how much is the maximum flow. It also is like the hard stop to your valve, meaning increasing pressure drop to any X number of bars may or may not lead to increasing flow. So it gives you a very real uh, understanding of what is the maximum flow that you can get. What it can give you is the choked condition. So as you have seen that FL can be determined using the choked condition, and it requires that the valve goes through cavitation. So even before cavitation, we can have a good prediction or a good estimate of how far we can push the valve or its boundary conditions or its process conditions, so that we don't get a choked flow, or so that we don't enter those cavitating zones. We also need FL to accurately model noise. So as we have seen in previous webinars, noise, even in various standards, BDMA or IEC standards, requires a good prediction of FL. It depends on FL apart from the other parameters as well, but FL is one of the key contributors to this evaluation. So for complex geometries, noise attenuation devices, anti-cavitation trims, it becomes very essential that you have a good value of FL. Then there's also a valve style modifier. So here, this is just one of the parameters that requires FL to be known a priori. So what happens is FD is basically how many flow paths are there in your valve, and it is required for some calculations, and this FD depends on FL. So without an accurate FL for complex designs. FD also is pretty inaccurate. And FL is again used in many such parameters for calculations. So it's a very important parameter to have a good prediction on. So we have seen how FL matters, how it's defined, what causes uh, the flow to choke. Now we'll understand how FL is actually measured. So we'll have a look at the physical flow loop test setup. In this case, what happens is uh, there's the pressure tapping at the upstream and the downstream. We start with a non-cavitating flow for the CV. Then we increase the pressure drop by some value. So in this case, we have increased it to this point, and then we either increase it or decrease it by a certain amount. So let's say we decrease it by 10% and we observe the flow rate. If the flow rate deviation or the difference between the case 1 and case 2 is within 2%, then we would say the flow has effectively choked, and the intersection of these two curves, the Qmax and CV that we got from the first, will give us the FL value. As you see, this is a very iterative process. So you have to run one with the CV, then you have to run with the second one. So we were lucky that, just in the two cases, it started choking. But you might need to go beyond that to, actually get a choked condition. And this is a very iterative process, even in physical flow loop tests. So challenges of flow loop tests are it's limiting in valve insights. You can get the FL value, but it won't give you any insights because you cannot visualize the flow inside a valve in these tests. Uh, it costs a lot of time, so there could be a waiting time for physical flow loop tests in laboratories, and there's a lot of cost involved. There's a lot of time involved, and the one of the biggest limitations is the large size walls. Large size walls cannot be efficiently tested. It will take a lot of time, it will take a lot of effort, and it's like a physical constraint. You cannot go beyond a certain valve size in the tests. Each lab will have its limiting size. So the other question would be, okay, I have the analytical methods. I can just use them. Well, they would work for very simple standard trim types. Uh, they cannot capture various flow phenomenon like flow separation, turbulence, different kinds of fluids, and even if you get these empirical formulas, it requires a lot of adjustments. If you go from, say, one design to the other to the next, it requires a lot of tweaking of the formulas and to generalize these formulas. So this is where CFD comes into picture. So CFD is a method by which you can model the flow or any transport phenomenon. So CFD is the science of predicting flow, and how this is done is we solve a governing equation and we apply boundary conditions, and the solver solves algebraic equations on small discretized domains, which we refer to as fluid volumes, and then it integrates the entire solution over a million of such discretized volumes, and we get to visualize the flow, heat transfer, or any phenomenon related to transport. So any species chemical reactions can be modeled and simulated using CFD. The challenges with CFD are that it requires a lot of expertise. We require a CFD engineer or an expert in CFD to accurately model all the steps and to choose the right solver settings to post process the results effectively well. Then there comes the hardware cost. So since this is a numerical setup, it uses high performance computing to solve the problems in uh, you know in less time, and HPC hardware might not be available with everyone. Then there comes the license cost. So CFD codes are pretty expensive to buy if you're just a entry level user. Even it gets added up. Even if you have a team of CFD people, this recurring annual cost. And uh, so this is the summary of the three things that we saw. We can either go with flow loop test, high accuracy, a lot of time, a lot of cost. Analytical methods, you will have a lot of compromise on the accuracy, but it will be very quick. The cost involved is very less, and the skill involved is moderate. CFD, it will be very close to the physical flow loop test. It will require time, but not as much as compared to physical flow loop test. It will require some cost. Again, not as much as physical flow loop test, and the skill required to run a CFD simulation is immense. This is where Autonomous Valve CFD comes in. Autonomous Valve CFD is the specialized app for Valve CFD simulations. So this is a virtual flow loop testing setup. It refers to the same ANSI ISA 7502 standards, IEC standards, and M49 manual for calculating flow parameters such as CVKV, CDT, which is the hydrodynamic torque coefficient, and sigma, which is the incipient cavitation index. It's the same index that we saw a few slides back, which is where the cavitation would start. So this technology is built on three powerhouses of technologies. We start with the viewer, which is the Autodesk Platform Services, where we can 3D visualize the 3D results, the 3D CAD files in real time. We use the solver OpenFOAM, which is used to solve the complex flow physics. All of this is housed on the cloud infrastructure, which is powered by AWS. And all these three things put together is what power the Autonomous Valve CFD. So what is the input for CFD? Well, it requires a 3D CAD model. Then the user will select the moving parts, and then it will specify the flow direction and will define the inlet and outlet. After that, the autonomous process takes over. It will do all the CFD related tasks autonomously. So no need for any manual CFD effort here. Just click a button and everything works. And as a result, we get a 3D visualization platform. We can visualize our 3D results. We get performance curves. So CV curve, CDT curve, all of these curves, which are the flow characteristic curves we get from the simulations, and everything from the qualitative and the quantitative aspect is consolidated in a automatically generated PDF report. So no hassle of extracting the results, putting them in a in a Word document, then converting that Word document, and all of these things are taken care of. So with these innovations, what we can do is we can really simulate complex parts, like additive manufacturing is taking over. So having complex part design is no longer a dream. It has become a reality with 3D printing, and complex trim designs can be effectively tested even before they are manufactured using Autonomous Valve CFD. So these images that you see are some complex designs that have been simulated using Autonomous Valve CFD. So we'll just quickly go through the demo. So this is the interface of Autonomous Valve CFD. We start with adding the valve details. So this is the first, creating your first simulation using AVC. And we upload the geometry. We support step file, parasolid file, .sat file. All of these files are supported. Then we'll specify the valve size, valve type, trim type, all of these things. Then we move on to selection of the moving parts. We'll select the moving parts. We'll select the shaft as well, select the axis. We specify the openings, and everything is automated. So it automatically created 10 openings without, with just a click of a few buttons. We also have an advanced feature which helps you to uh, accurately capture such complex trim designs. So we'll specify the flow direction and we'll now submit the run. So once we submit the simulation, the autonomous platform takes over. It will automatically do all the CFD related tasks, which starts from fluid volume to meshing to solving to post processing. And at the end of the results, you'll be able to visualize them. So this is the streamline. You can see the complex flow patterns through the disk, through the trim, through the valve. You can play with the angle of openings, then it will change in real time. You'll see how the velocity changes, how it changes the direction. Similarly, we can visualize the pressure. We also can visualize the internal surface pressures. So where there is a high zone, high pressure zone, where there is low pressure zone, everything can be visualized. Then we also look at the contour plots, which gives you the real insights into the flow physics. So you can see how, high velocity jets form in this uh, particular simulation. And, you can see any cut section that you wish, you can just take, you can visualize, you can really dive deep into your design to actually understand what's the physics that's taking place in this. Then we come to the quantitative part of this. You get a nice tabulated result. You also get a nice graph of all the results. So all the CVs and are plotted against the opening, and you can even export them. You can add it in your Excel sheets. You can document it. You can even download it as a PNG. All of this is consolidated in a report. So this is the automatically generated detailed report for the simulation. No manual intervention here. Everything is noted here. Everything is added here. The valve type, the roughness, the executive summary, it gives you the results, it plots the graphs, it gives you a detailed analysis of these things. It also adds the CFD process we followed. We plot CV, KV, head loss. So this was a globe valve, so there's no torque here, but even we are plotting that. We visualize this and we also give you the incipient cavitation index, and everything is nicely summarized in that report. So this is the power of AVC. So as I had promised you in the earlier sections, we have some exciting case studies for you. And I would like Joel to present and tell us more about what these case studies uh, are about.
Yeah, thank you, Akshay. So, in this case study, we will be looking at the impact of cage trims in glow balls. So, there are two glow balls in this gauge study, one with no cage and one with a cage, and both the valve models were ran with the same case setup. So what we observe here is that the FFL value remains consistently higher across all openings with a cage system as compared to a globe wall without a cage trim. So as we had seen in the previous slides, that as FL values go lower, higher the tendency for the valve to cavitate. So looking at the pressure versus length plots, or that is the pressure, how it varies across the valve from the inlet to the outlet, we can see that the pressure recovery downstream is much higher as compared to the pressure recovery downstream in the case of the globe valve with a cage stream. We can also see that with the cage stream, the pressure drops in stages rather than dropping all at once. And we can also see that if we add more cages in globe walls, we will be able to drop the pressure in more stages, further dropping the pressure in stages and therefore bringing the FL value closer to 1. So this case study concludes that having a cage trim in a globe ball or having a device which reduces the pressure in stages helps in maintaining a higher FL value across all openings in a valve. So now in the second case study is about the FL comparison between a globe valve and a butterfly valve. So as we can see that both valves have a similar CV value, so therefore that would be similar flow capacities, but are very different when it comes to an FL standpoint. So as we can see in the FL versus opening condition plot, a globe wall generally maintains a flat or a consistent behavior across all conditions, but the butterfly valve varies across the opening conditions. So as we had seen in the previous slide, a butterfly valve at a fully open condition has a lower FL value compared to a globe valve. And obviously this is because the internal geometry of the valves in a fully open butterfly valve, it is essentially a straight pipe. Whereas in a globe valve, the flow path essentially bends at the trim before traversing downstream. We can also see there in the plot, which represents the pressure across the length of the valve, that as compared to the butterfly valve, the pressure recovery is lower in the globe valve. So we can also conclude in this case study that at lower openings, a butterfly valve may be safer, but at higher openings, particularly at the fully open condition, a butterfly valve is more prone to cavitate as compared to a globe valve.
That was a very insightful case study, Joel. So this really brings the point to home, meaning given a choice between CV, where a user could go for any design, and that would ensure the flow capacity. But what really affects the flow capacity at uh, the given process conditions would be the FL, because one valve would perform much better subject to the high pressure drops as compared to some other valve. So FL becomes a deciding factor in your choice of valves. So we have seen the case studies, we have seen how AVC works. So a genuine question to ask is, well, have you, how can we, get the trust on these values? So uh, we have done extensive validation studies. We'll have a look at it. So this plot shows you the accuracy of CV prediction using AVC as compared to the physical flow loop tests, which were conducted in FCRI and in Utah Water Research Lab. The types of walls simulated are, there are various types of walls. If you look at the CV, there are various sizes of walls, and all have been noted to have efficiency between this 90% accuracy band. Even more so, there's a concentration of plots of points where it's even up to 95%, in some cases it's 100% accurate. So accuracy wise, at any given simulation, at any given valve, at any given opening, we lie in this 90% accuracy bands. So apart from this, regarding FL itself, we have done some validation. So this is for a cavitator disk, and we have validated our approach for the FL as well. So if you can see here, we went in a iterative fashion and we validated that the FL from the test data for this and AVC were 99.7% accurate. So to drive the point home even further, this is the power of AVC, is that you can run different valve openings within a matter of hours. So CC Tech, when it started as its initial days, used to do consultancy for various valve manufacturers where we used to get CFD projects. And at those days, we used to compute the CV within a week because it required manually doing the cleanup, doing the uh, meshing, solving. Then again, you have to rotate the part, do all of this repetitively, and then you get the results. Then you have to put those results in a good PDF, and then you have to submit the results. So all of this took about a week, but with AVC, you can do it within an hour. So the time required to do simulations and to do valve performance testing with AVC becomes, much easier and at a very reduced time. So how does AVC do this? We'll quickly go through it. So what AVC requires is the input CAD model. With the algorithm, it will use the correct meshing parameters, correct CAD cleanup, and it will host everything on a 36 core instance where it will run simulations. And as the result, you get qualitative as well as quantitative results. This is how it works in parallel. So each opening gets a dedicated server, dedicated instance, and all of the 10 openings or all of the 9 openings run in parallel, do all the parallel computations, and at the end give a nice consolidated qualitative and quantitative results along with the consolidated report. Let's say you have a number of designs, even then it would parallelly work and compute everything in the same or a similar amount of time, meaning you start 3 designs and they would complete in the same amount as it would take to complete one design. So this is the real power of AVC, where you can do design optimization studies, design validations very easily. The thing that would take a month for a CFD team to do, it's done within a matter of hours now. Then there's the cross country collaboration. You can collaborate with many teams from many different regions on the same platform and share your results, share everything from the report to the visualization. Everything works harmoniously in AVC. So just to compare, conventional CFD requires an expert, a lot of manual process, limited in-house resources, leads to results in days, whereas AVC, the autonomous process takes care of the entire CFD process. It runs on expandable cloud computing, meaning no longer you have to worry about the hardware limitations, and result within hours, which again costs pretty less. So ultimately, AVC leads to much quicker and easier valve performance evaluation. So this is what we get in AVC. So this is a qualitative side of the visualization as well as the quantitative side of the results. We have also added features so that complex trims like this can be easily simulated in the app, as well as we also have added incipient cavitation index, where you can get the incipient cavitation for each of the openings and make informed decisions using these values. So shout out to Praveen Kumar, who used to use this analogy. So I'll just follow the same. So let's say you are gardening in your backyard and you want to plant a few samplings. So what would you rather use? Would you rather use a JCB, or you would rather use effective gardening tools? So JCB is the analogy for CFD softwares, general purpose CFD softwares, where they handle everything from an inviscid flow to complex multi-phase flows with moving bodies. But AVC is very tailored fit for valve simulations, meaning it's a efficient tool that takes care of the valve simulations. So a few customer success stories. So these are our proud subscribers, and we'll talk about Bray just for a quick success story. So Bray is one of the biggest wall manufacturers in North America, with over 40 offices in various countries. It has over $1 billion year-on-year growth. So they have multiple design teams in different parts of the world, and this is where things get interesting. So physical flow loop tests for Bray used to take a lot of time. There was a lot of waiting time, and generic CFD tools or commercial CFD tools used to, be limited by the hardware, by the license, and the expertise as well. So a CV curve would take, as I've already said, 5 days to a week for one design. So with AVC, they started in 2019, and for the past 5 years, we have been renewing. They have been renewing the subscription for AVC, which gives us a lot of joy because we have learned a lot over the years from them. And from the user point of view, they started with 3 users. Now 30 users across different teams are using AVC, and we have tested over 1,200 valves for uh, using AVC. So the cost benefit of AVC is, it's tremendous. Experimental setup would take exponentially more cost to do it, and it would take a lot of time as well. And ultimately, we also save a lot of energy. It saves in terms of physically running the valve, labs, transportation, all of these things. It's taken care of. So these are a few pictures from the visits that we make with our customers. We interact with them to understand industry problems and how we can solve them effectively. So the man himself, Mr. Brindesh Ruwa, he has spoken a few kind words about AVC and his experience with it. So it accurately predicts fluid flow characteristics like CV, KV, CDT, and reducing the need for expensive physical prototyping and testing. So, this is the whole philosophy behind AVC. So as a part of the attendance of the webinar, we have a special announcement. So you can log in to AVC and start your first simulation. And in case you need any assistance, you can hit us up and we will definitely support you through the process of running your first simulations and, taking things forward for you. So for webinar attendees, we have a 1 month free subscription, which usually would be a free trial with 20 credits. But since you have been so kind to attend the webinar, we would be giving you 30 simulation credits to go through the app, have the experience for yourself. I'm pretty sure you would enjoy the experience. And that's it. Thanks everyone. Thanks for joining the webinar. And we would move on to taking up questions. Uh, Rahul, Joel, any questions we have from the participants?
Yes, there are two questions in the chat box.
Okay. So, I'm reading out one question. How directly can FL be used to predict cavitation onset compared to cavitation index or sigma? So, FL would be used to predict the choked condition. So, to predict onset of cavitation, we have the cavitation index, which is called incipient cavitation index. But to have the prediction on the other cavitation indices, FL can be used. So there is a very well-known correlation between FL and choked cavitation index. So you can use that relation to predict the choked cavitation index. But FL is essentially used to predict the choking condition or the maximum flow condition through the valve, meaning what's the maximum your valve can go through. And since FL, to compute FL, the valve will go through, in the test, the valve will cavitate and it will go through incipient cavitation, constant cavitation, choking cavitation. But you really don't need to do that. You can just, with the FL parameter itself, you can have a prediction. So using FL, you can compute, okay, what's my choked condition or what's my choked pressure drop is. And then you can say, okay, if this is the choked pressure drop, my valve should not enter this zone. So it's a predictive mechanism. The second question is, can FL be modified effectively through trim design to mitigate cavitation without significantly affecting CV? Yes. So as Joel discussed in his case study, we saw that FL increased quite significantly after addition of the cage. So it reduced the likelihood of cavitation. So yes, you can modify trim designs. You can add a few things. I wouldn't say it would affect CV. It will definitely affect CV because you are adding more obstructions into the flow path. But that's the trade-off that we have to make in the long run. Would you rather have a effectively working valve rather than a valve that breaks down and you have to replace the parts, you have to replace the valve? It causes a lot of downtime in the industry. So that's the trade-off. But I think that's a good trade-off to have. Then there's another question which says, when using CFD, how accurately can FL be predicted compared to experimental data? So as I've discussed earlier, so CFD can model flow and predict CV and FL very effectively. The question is, FL inherently takes a lot of iterations to run. Even in physical flow loop test, FL cannot be determined unless the flow is choked or it starts choking. And to get to this choking condition, a lot of high fidelity multi-phase simulations have to be run, which takes a lot of time and a lot of computation power. Along with that, it also takes a CFD expert to run such simulations because with complex physics, we have to model things accurately, choose the right settings for the solver, and this is a very extensive and time consuming process. But with AVC and with the Simulation Hub team, we have devised a methodology which can give you a very good estimate of FL without the hassle of high fidelity multi-phase simulations. So I think that's about it. we have reached the end of our webinar. I would like to thank all the participants for joining the webinar. I really appreciate it. And I do encourage all of you to start your trial accounts, log on to AVC, give us a quick message. We will, get back to you if you are facing any challenges. Try the experience for yourself. I'm pretty sure you will love it. And in case you have any queries regarding cavitation, FL, noise, CV, you can write us with an email, and we'll definitely get in touch and answer all your queries. So thanks once again. Thanks everyone. Have a good day. Have a good night. Bye bye. See you for the next one.